So I think we're ready to get started. Please take a seat. Rao Kambanpati is a professor of computer science at Arizona State University, and he is currently president of the Association for the Advancement of AI, the IEEE organization, and a trustee of the Parent Partnership on AI. His own research focuses on automated planning and decision-making, especially in the context of human-aware AI systems. He is an award-winning teacher and spends significant time pondering the public perceptions and societal impacts of AI. He was an NSF Young Investigator and is a fellow of the IEEE. Please welcome Rao.
Thank you all for coming, and thank you, David, and the organizers for inviting me. Setting up the perfect weather and outdoor Wi-Fi that an AI researcher can ask for to prepare his talk. So that's pretty much what I was doing. So I was going to talk to you a little about AI and why it is so much in the public discourse these days. It's mostly sort of technical, but also talks a little about the societal impacts that some of you might be thinking about. So anyway, I've been in this area in AI for quite a while. That's my 1983 bachelor's thesis on speech recognition. You can see that the laser printers weren't invented, and I should do my nice own drawings. And most of my time when I was in AI, people sort of felt sorry for me because it looked as if I could have done something better than AI. And in fact, if there was a Google and you looked at AI, you would have gotten something like artificial insemination as the top hit. Okay, and in fact, during my time, most of the things that were going on about AI was all these physicists, Roger Penrose and various other people talking about why AI is not possible. So it was, you can imagine being a grad student and working in a field and here realizing that the top minds in physics are saying, you should look at doing something else. Now, things have changed a little of late. I assume you realize that. So this is an interesting curve showing the number of companies that are mentioning the word AI in their quarterly earning reports. And you can see that around 2008, quarter one, that was close to zero. And then that's quarter four of 2016, you can see where that's going. If I had 18 and 17, they would be out of the curve. So clearly, there's a lot of interest in AI, not commercial as well as public interest. In terms of public interest, Obama, the previous president, said, my successor will govern a country being transformed by AI. Many people think that we're already there, AI is probably governing us. But certainly there was interest at the national level about what AI is capable of doing. And then these days, every possible commercial consumer item that you can use has to say it has AI in it. So for example, the Colgate electronic toothpaste apparently provides real-time feedback to improve the brushing habits and then prevent problems and so on. So you can imagine how much AI has, and it uses AI algorithms to do that. So you can imagine everything has to use AI these days. Now, things have gone a little more than that. I mean, I think that's sort of commercial interest. We have also started gamifying AI. One of our own researchers, Andrew Wen, said AI is the new electricity. Okay, and then Sundar Pichai, who is the Google head, didn't want to be left behind and said AI is bigger than fire and electricity combined. And then there's a guy called Tony Landowski. I don't know if you know him. He was the guy who left Google and joined Uber and then got disgraced, but he had a lot of time on his hand, and he has been talking about AI being a god. He actually started a church for AI. So, so this is not simple science and engineering we're talking about. Now, okay, that's all green, that's all good stuff. There are some slightly worrisome things. Elon Musk has been talking about AI a lot, and he considers himself an expert. I'm not quite sure why, but one of the things he has said is AI is a bigger threat than North Korea, and AI will start the Third World War. This is what Elon Musk was saying. Then Stephen Hawking, the renowned physicist, has basically said AI could be the worst event in the history of civilization. And then, of course, Alan didn't want to be left behind, and he said, AI is likely to destroy humans anyway. What are you talking about? Civilization. So, I don't know about you, I am a little worried. So, I think one of my colleagues, my collaborators, Julia Batcher, might be in the audience, and when I visited her in Johnson Space Center, I kind of tried to see if I could make interstellar travel and get out of Earth. If you are also worried that maybe that you have to run, you can be fine for this talk alone, because it turns out that apparently the robots are worse skiers than I am. So, right? So I think you'll be fine. So you should not worry about it, at least during this talk. And of course, I'm not complaining about all this hype. Without the hype, why would I get onto TV and get called to give you guys talks in this beautiful place? Okay, so that's sort of the preamble. What I want to do today is like 3 parts, depending on the timing. One is what just happened, and why is it that AI is so much bigger in the public consciousness right now. Okay, I want to give you some perspectives that are very useful, because some of you are probably already working in AI applications of AI to aerospace or space. For you, maybe it's sort of obvious, but some other people it may not be. So I want to give you some perspectives on why it is, what exactly happened, and what's the best way to think about the technical advances that are happening right now. And then I want to talk about, are we done yet? If you look at the news items, I made the mistake of telling Google News Tracker to send me any news articles that have the word AI in them, and so I haven't gotten any work done since then, because every morning there is so much news items. And so the question is, are we done yet? And I want to give you some idea of what are the thresholds that we still have to cross to get to something like human level AI. And you need to get to human level AI before you can start worrying about Stephen Hawking's and Elon Musk's worries of superintelligence. And then I actually, one of the thresholds that I will talk about, and if I get a chance, is something that's close to my heart, my own research area, which is actually getting AI systems to collaborate with humans. I'll try to explain to you that AI had this bit of an ambivalence towards humans. We weren't very sure whether we were trying to replace them or augment them. And so it turns out that actually augmenting humans has a lot more interesting challenges, and I want to say something about that. And then, depending on the time, I also want to touch upon how are we going to be able to manage the risks and the rewards of the current AI technology. I'm not really interested in superintelligence worries. If that's what you really want to hear, listen to Elon Musk. He's very good at that. So I think there are important worries about the current technology because of the power of the technology, and it's worth thinking about. So that's what I hope to do in the time I have. Okay, so let me start with a very simple definition of what artificial intelligence is. And the general idea, the way we do is they sort of give a circular definition in the textbooks that the goal of AI is to make machines or software artifacts that show behavior which, if shown by a human, would consider it to be intelligent. So obviously that's sort of a circular definition. And the way in introductory AI courses we talk about intelligent agents. And intelligent agents sort of looks like that particular black box diagram. So it's basically keeping track of the world by sensing its state and then it's doing some reasoning about what it knows about the world, what it just found out, and then based on its goals, it's trying to do an action in the world. That turns out to be like the most important thing. So if you don't want to just be a spectator, but want to change the world, you want to live, then you have to actually act in the world. And so this agent has to act in the world. So that's the notion of an intelligent agent. Okay, keep that in the back of your mind. And I want you to think about, since after all, we are the ones who are obviously the intelligent creatures, at least according to us. So it would be useful to think in terms of how humans, actually human babies in particular, baby there, show signs of intelligence. You know, some of you probably have grown kids and you still think that they are not showing signs of intelligence, but normally the way you would go about seeing this when you have a small kid is you see these kids come into the world, start showing perceptual intelligence. They will be able to recognize the faces of their parents. It's very hard for kids to survive if they don't recognize the faces of their parents and show, and smile at them. Okay, and then they will start doing manipulation, not just manipulation of the parents, but manipulation of physical objects. So for example, this was a little kid who is the daughter of one of my wife's PhD students, and I remember we went to this lunch and she was doing very, very involved fine motor skills in actually looking at various small things on the table in the hotel, in the restaurant we were eating, and there are no robots that are still able to do that. And that's an indicator, okay? So they do that, they actually do image recognition, hand-eye coordination, and mostly what they're doing is this tacit intelligence. They do it, they don't necessarily have a theory of how they're doing it. Even if they do, of course, they don't have language to tell us. Okay, and then they start showing some emotional intelligence, smiling at people, crying all the time, and all that stuff, and then show some social intelligence, not biting, kids around you and stuff. And then finally, if you have money and they go to school, they start showing cognitive intelligence, reasoning intelligence, and they start taking SATs and maybe go to colleges and so on and so forth. This is typically the way we see intelligence being shown by human beings. Keep that in mind. Now, the last time around, people used to call us AI folks to come and talk to people outside of AI was in 1980s, when there was a big expert systems craze. And so in 80s, there used to be these expert systems, which were these rule-based systems. Somebody has an idea about how to solve certain problems in either diagnosis or in law or in some manufacturing or in NASA, for example. And then they would actually write these as rules, and basically these expert systems would reason with them and then solve problems. That was like a huge, big, hype and book about AI, and back in the 80s. Okay, in the 90s, you heard about AI when Kasparov got beaten by Deep Blue in chess, right? Until then, somehow chess. I am a bad player of chess, and I always consider chess not to be a sign of intelligence whatsoever. But a lot of you seem to think so. And when Kasparov actually got beaten by Deep Blue, obviously that was a big news, and you all heard about that. One of the interesting things is in 97, when Kasparov was beaten by Deep Blue, it was able to do very powerful reasoning about what move, if it makes now, will lead to a checkmate maybe 7 moves later, for example. And that's actually a pretty hard thing to do. Most people cannot do that. And the machines were able to do that, but they had no clue what each piece, they could not look at a piece and realize that this is a pawn, this is a knight. And they certainly could not actually hold them and place them from salvation. Okay, so essentially that's what you want to keep in mind. So basically they did not have motor skills, they didn't have perception. It's only in 2000s, and more recently actually, in around 2010 onwards, we started making pretty big strides in perceptual intelligence. Machines now can see, machines now can hear. They still can't manipulate objects anywhere near as well as they can see and hear. Okay? But that is the biggest thing that happened in the most recent times. Okay, and currently, of course, in the technical field that we are in, what we focus on is trying to connect reasoning and perception. So basically, these different parts of the intelligence. That's what we wind up doing. Now, of course, many of you, at least not many of you, many people outside have heard of AI most recently because of this perceptual intelligence. And you'll find out that perceptual intelligence basically, we ourselves don't know how we see the world, and so we just have to learn how to see the world. And so many people actually outside think AI has just started like 5 years back when they started reading about it in New York Times. And so that was my sort of AI aphorisms I've been doing on the side, a set of AI aphorisms that I'll show you. But that's basically, if anybody tells you that, oh my God, one of these days AI systems will start reasoning too, then you should basically tap them on the shoulder and say, you also, they have done reasoning all the time. The question is combining reasoning and perception. Okay, now here's an interesting thing. I showed you this picture earlier, and the humans went this way. Human babies started from perceptual intelligence, then they did manipulation of physical objects, then emotional, then social, then cognitive reasoning analysis. I just showed you in the previous slide that AI systems went this way. They did reasoning first. They were able to solve chess. They were able to do expert reasoning before they could actually see anything. In fact, one of the biggest expert systems examples was MySim, which was an internal medicine system. And the joke goes that you could essentially describe to it the problems that you are having with your Volkswagen car engine, and it would happily diagnose its internal medicine problems because it had no clue as to what actually was looking at. Okay, but so the point is that it's important to look at this picture because it actually puts in perspective a whole bunch of things that you see in the public domain in terms of the discussions about AI. The fact that human intelligence went this way and machine intelligence went this way is something that you want to keep in mind. And if you keep that in mind, I argue many things fall in place. Okay? So for example, why did AI develop in this reverse order? Why didn't we develop the way kids develop? Why did AI systems develop the way kids develop? Well, it turns out, not surprisingly, that it is easier to program computers on tasks that you know how to do consciously. And there are many things that we actually know how to do consciously, and for which we could write programs. But there are also many things that we do without knowing how we do. Right? Looking at a face and saying, this is my mom, or this person is smiling, or this person is getting bored with me. Those are things that we seem to know how to do, but don't have a theory. We can't write steps as to how we get. Okay, so it's not surprising that in the beginning we had to do programming of the computers, and that was done for the tasks for which we had explicit theories. And then it turns out that perceptual intelligence and manipulation intelligence, there are no rules. It's very hard to write a set of rules as to how to look at the world. Because of which, actually, we had to do perception and manipulation the same way people do. And here is a little thing to understand. Your kids, when they come into this world, they spend a whole bunch of time doing nothing, just being cute. Okay? And evolution has, messed around with our brains that we think that these jobless kids who are just being cute are quite cute. And so we just let them be, and they're sucking up essentially experiences and learning from them. They're learning how to recognize the world, they're learning how to do voice recognition and so on. These are things kids were doing, and they basically are doing learning, and machine learning systems have to come of age before you could do improvements in perceptual and manipulation. It's a very useful thing to know, and it's also important to know that you need both. You need system 1 and system 2. You need the ability to look at the world and see it and hear it, as well as the ability to do deep reasoning. It's not one or the other. Now, the other interesting question is, why did AI catch public imagination now, given that it's been around for quite a long time? In fact, many fields cannot tell exactly when they got their name. You have no idea when physics was named physics. And I don't know that you know when aerospace engineering was named aerospace engineering. AI can actually say exactly when it was named AI. In 1956, there was a conference in Dartmouth, and these four guys, Martin Minsky, John McCarthy, Alan Newell, and Albert Simon, essentially did this conference, and McCarthy basically came up with a name on artificial intelligence. As a historic side note, it turns out that there was an area just quite close to what AI was trying to do at that time. By Norbert Wiener actually was doing these things called cybernetics. It turned out that McCarthy could stand Norbert Wiener. So he said, I'm not going to say anything about cybernetics because then Norbert would be talking to me. So I just named it something completely different. He said the artificial intelligence, which led to a lot of grief to lots of us. For example, my colleagues kept, used to ask, you must be doing AI because you are missing the natural, intelligence. But of course, who is being flown to come to Big Sky now? Right? Okay. So the thing is that early AI was a blind and deaf Socrates. Imagine having a kid who could play chess but can't smile at you, can't recognize your face. Evolutionarily, those kids would have not had a chance. AI systems were like that, essentially. Perceptual abilities allowed AI to come to all of us. They're right now on your cell phones. Okay, you could basically take pictures, you can recognize pictures, you can do voice recognition, you can dictate to your cell phone and so on. That made things, AI technology come into the hands of everyday users and the entire public. And that changed what people can think of about AI. So that's something that's very useful today. So now, of course, now people suddenly see AI everywhere, which also leads to all sorts of misperceptions, some of which I've talked about, such as, I got the robots are going to come and get us very soon. Okay, but it's really useful to understand that what we really changed is we started making big leaps in perceptual intelligence. Okay, so I'm going to say a very few slides about the specific technology, basically called neural networks, that has led to this most recent improvements in perceptual technology, vision and voice and so on. And it's actually quite useful to see that also because historically this is an idea that almost was there from the beginnings of AI. The neural networks were under the name perceptrons were being done in 1960s in Cornell by this guy called Frank Rosenblatt. So in fact, the current neural network craze is basically called the third coming of neural networks. So they were around in 60s, they were again around in 80s, then finally they came again in 2012. Part of what I'll try to explain to you is why did the third coming actually become the magic coming? Okay, why is it that has used to before? But so for those of you just who probably haven't heard of neural networks, maybe very few of you, I just want to point out that these were essentially kind of loosely, extremely loosely inspired by the brain architecture. And we know that they have neurons, and we know that they tend to have a shouldering. That means they basically, when there is the input activations reach a certain level, then the neuron fires and sends signals to the connected neurons. And so basically, the idea that we're trying to do is to combine these neurons, each of which essentially have inputs coming in, and they're multiplying those inputs from different inputs are coming from different other neurons that are connected to this. They're multiplying them by some weights. These weights have to be decided, and then you're sort of summing these weights and doing a nonlinear function on it. Okay, so typically a thresholding function, but pretty much any nonlinear function. So you can think of this as a thresholding function, and that you could say at some loose level kind of corresponds to like a neuron in the human brains, and people were sort of enamored with it. And there are some interesting theoretical results about them. For example, it turns out that neural networks are universal function approximators. Any real valued function you can think of, there is a neural network that will essentially approximate it. Okay, and in fact, it's what's actually more interesting is a neural network with just one hidden layer to be able to approximate. That means that 3-layer neural network can approximate any continuous function, and 4-layer one approximates any unitless continuous function. So that's a pretty powerful theorem, except it's an existence theorem. It doesn't tell you what that neural network is and how many units are there. So people have been enamored with it, and learning neural networks is figuring out what these weights are. That's what we're trying to do. Okay, and these weights are learned via gradient descent. Obviously, if you're all engineers, you know neural reflection methods, you know basically using calculus to find the minimum of a function. So you are essentially trying to find the minimum of a error function by gradient descent. And about the only interesting thing from a neural network's perspective is that you can take the error and back propagate it such that you have some idea of what the errors would be at the intermediate nodes, and then the weights are changed in proportion to those errors. That's basically what you end up doing. Now, that actually is just chain rule of differentiation, which is again elementary calculus. The previous one is the simple neural network architecture. The things that people have been doing is looking at different kinds of architectures that actually might be more effective in the sense that you have to learn fewer weights. So this is what's called a fully connected network. This one basically is a convolutional network which sort of tries to use the same weights multiple times. So for example, the same set of weights are being applied to different regions of the image. The question, of course, is what are those weights, and that's supposed to be learned during the learning phase. Okay, and that's what convolutional networks do. And in general, you can say that everything that a convolutional network does, a fully connected network can do, except this does it with much fewer learned parameters. You get to learn much fewer weights. And the number of weights you have to learn, if you have to learn lots of weights, then you need lots of examples that you have to see. Typically, what you will wind up doing in this training is you will have some set of training examples where for each example you know what the inputs are and what the output is. You clamp the inputs, you let the network say what the output is according to it, what it's supposed to be, and you see the difference between the true output and what it's predicted, and you take that error and basically backpropagate it, and then change the weights. So that requires lots of examples. And the more the weights, the more number of examples that you need. Anyway, so these sort of convolutional networks are like extremely powerful now. They wind up being used in all the image recognition software. One of the interesting things is computer vision as a field used to basically look at these kinds of filters, and they would have names, different named filters, median filter, R filters named after Geber, and so on. What happens is the filter weights right now are being learned automatically by the network. So the entire business of getting filters named after you went out the window because the machine learning systems are just learning unnamed filters. That's basically what's happening. And by the way, computer vision as a field has sort of become a sub-discipline at best of neural networks right now. Okay. Now, in terms of image recognition, which is where people started hearing a lot about originally about neural networks, one of the things that people found is the deeper the network. Remember, I just showed 4 layers, 3-layer networks. The deeper the network, the more the number of layers, the better the network performance seemed to be. That's kind of an interesting scenario. In particular, there was, starting around 2012, which is exactly when that AlexNet basically beat existing computer vision systems by just learning directly from the examples. And AlexNet was a sort of a convolutional network. And this particular competition was set on ImageNet, and I want to say a couple of words about it. ImageNet essentially currently is about 14 million images of different things, classified into 1,000 different categories. It so happens that 200 of these categories are dogs. Keep that in mind. So, when you sleep, you dream about people. Neural networks can be easily made to dream about dogs because they have seen 200 dogs during their training, because most neural networks are actually trained on ImageNets. And this is not a joke, actually, this is sort of true, because there's this whole idea called deep dreaming which where you essentially make the network dream by changing the image, and they find it easier to dream about dogs. So dogs in clouds, dogs with funny faces, dogs with all sorts of things. It's much easier because they've seen many more of those examples. Now the interesting thing here is in vision, on this particular data set, computers are already superhuman. By back in like in 2015 or so, the error rate for the neural networks which had 150 layers, which actually turns out to something like 14 million different weight numbers that the network has to learn. This is nothing that you're going to sit down and write. Okay, you have to learn. Okay, and so that network had a 4.95% accuracy error rate, and humans had 5.1% error rate. Now, if you feel very sorry about humans that they're losing to networks here, first of all, it's worth noting that in narrow spheres, superintelligence already exists. Machines do quite well in certain things compared to us. They do much better arithmetic than us. They do, for example, calculus better than us. So what's different is we can do general intelligence. The second thing, of course, is I'm not really sure I want to do well in a world where 200 of the categories are dogs. I can pretty much tell about 5 different kinds of dogs apart. And so the machines can do much better than me, and probably that's okay. One of the interesting things that I kind of was touching upon is why does gradient descent work? Which is this back propagation, and somebody called this back propaganda. Basically, why does this work at all? It's kind of surprising that when you have 150 layer network with 14 million weight parameters that have to be tuned, why do you think that this thing is actually working at all? In the beginning, people used to assume that gradient descent will have all sorts of problems for neural networks of larger sizes. To be fair, actually, back in the 80s, when people were looking at neural networks, they at most look at like 5-6 layer neural networks. And that was hard enough for them. And I'll explain to you in a minute why that was the case. It turned out that many worries, and then they also assumed that gradient descent will get stuck in all sorts of local minimas. Now, of course, you're all engineers, you know that our intuitions of high-dimensional spaces suck, right? So 14 million weights means 14 million dimensional space. Do you have a sense of how that space looks? If so, I don't have a 4-dimensional space idea myself. So 14 million dimensional spaces, it turns out one of the interesting things is it's actually hard to find closed minimas because they have to be closed from all directions. So you're more likely than not are going to have minimas that are open on some sides. So it's sort of like between a minima and a certain point. And so actually the gradient descent can escape. This is one of the speculations people have. The other very interesting thing is what I'll say in a minute, which is that in fact, it turned out that small changes being done over a large number of epochs can actually make the network converge pretty quickly. Okay, so when I teach this the first time in the class, in Intro to AI, I ask them to think about something like coral reefs, which are extremely hard to believe are being made from the poop of these little things. But given deep time, that can happen. Deep time can be speeded up with computers because you can do millions of epochs very fast, and that is basically one of the reasons neural networks work very well. So why is the third coming of the neural networks a charm? It turns out that this is actually a slightly dated slide. About 2 years back, Jeff Hinton, one of the guys who actually kept on working in this area, even though everybody said you're crazy, you should just move on. He basically came to talk about this at IEEE, and he pointed out that now we can do 10,000x speed up in 3 years. Okay, and there are theoretical reasons. There are some infrastructural reasons. And the theoretical reasons include things that I won't go into too much detail here. For example, we figured out how to reasonably initialize the network such that the network won't get saturated. The saturation, if you need in a metaphor, think of amplifiers getting saturated with new distortion. And then we also figured out that the usual kind of continuous sigmoid functions were not as good as thresholds, and in fact, the linear ReLU functions which is basically actually discontinuous, is pretty good. Okay. Yes. Okay. 5 minutes. Okay. And then so then the other thing, of course, is that you could do techniques to avoid overfitting, which I won't go into. But the other thing that really is useful to think about, particularly, is that advances in data and computing infrastructure have made big difference in the amount of data that is available. This is kind of hard for people to understand. While AI people were doing what they were doing, the world continued to evolve. And I don't know, those of you who have seen Blade Runner, the first one, if you go back and see it again, you'll be surprised at how badly they were off in terms of how big their TV screens are and how big their phones are, because they just didn't see that coming. So within AI, basically, as AI people are working on these things, we have the cell phone technology and the internet, and we started capturing data. And the data wound up being useful in training the networks. To put this in perspective, actually, the old time, in the old days, computer vision used to work with just one image called the Lena image. And now I told you, even the benchmark has 14 million images. Google, etc., trained their networks on billions of images. Now, is this because we started making more data? People keep talking about the fact that we are making 14 gigabytes of data a day, each individual. The reality is we were always making data. Nobody was capturing it. I used to think, I would like to think that United was basically dragging passengers through the ice before too. What changed is we now have cell phones and we know that they're doing it. And so the data capture wound up changing the equation quite a bit. And to put this in perspective, the theoretical advances led to about 100x speed up, and the data changed. Just the fact that there is more data available led to 1000x speed up. And this was in 2015. So now you can imagine how much extra data we are getting. Two other things that are useful from this point of view that I want to mention. There are these things called GANs, which are a different kind of a neural network. And what they try to do is they have a dual-link network architecture where there is a generator network, which is a convolutional network, that starts from random noise as input and tries to generate images. And then you have a training set of images, like say cats or Hollywood actors, okay? And then the discriminator is given images from here as well as images from here, and the discriminator has to say whether the image is a real image or a one that the generator made up from scratch by fake. And it turns out that both of these are feed-forward networks, and they can actually be trained by the same gradient descent. That's like very surprising. And because of which, if you have enough data, these GANs wind up generating alternate reality. I'll show you some examples, generating alternate reality. So if you give you input, a GAN after training can generate, like, if you give inputs with horses, it can generate, inputs with, outputs with, zebras, okay? This one, input with an image, NVIDIA basically can just generate the same image, how it would look in summer, or in a day. Now, you shouldn't be surprised. You can, if you see an image, you can imagine how it would look on a sunny day. It's just that that's the same sort of projection you GANs can actually do right now. But this one actually, this is my home in the morning, and this is where I am today, right now. That GANs can't still do, you need planes for it. This one is interesting. This is a bunch of faces that are generated by GANs which have seen enough Hollywood glamorous types. All of these are apparently fake. But I'm sure many of them are making good money already, as we say. Okay? So the interesting thing is that this you can imagine, now that you can generate this, you can imagine what sort of impact it will have in actually manipulating reality. There is this old saying that if only people didn't have eyes to be sure with, they would be much harder to fool. And once you have eyes to be sure with, you will start actually falling for this sort of made-up reality, and that will lead to all sorts of interesting questions. There's also, different kinds of other networks like recurrent networks that I won't go into, but have been very useful in natural language processing. So I would actually obviously have to go very quickly. I need the second one. I still have a total 7 minutes.
We're at the start of the Q&A period, so you can go as long as you like for 5
Okay.
minutes or so.
Okay.
And after you do.
Okay. So are we done? Actually, when we're done, we'll be done soon. So one of the things that's been happening is this sort of relational exuberance. People have found that perceptual intelligence works well with neural networks, so they're actually thinking that everything will work well with neural networks. So give me a big enough GPU, large enough data set, and deep enough network, and I'll create you super intelligence. That's sort of the mantra that's going on in some circles. I want you to think of the following thing. This is a useful thing, which is data versus doctrine tension. As I mentioned earlier, intelligence both involves tasks for which you have explicit theories and tasks for which you don't have explicit theories. Currently, perceptual intelligence-based software is working off of tasks where you don't have explicit theories. So you only have data, and it tries to figure out what the theory is. But if you say that's the only game in town, then it will get you into situations where you will join a company, and the company will try to give you, here is the doctrine that we follow, these are the rules we follow. And you say, no, don't give me any rules, I'll just watch you for about 1,000 years and figure out what you do. And that way I feel good because I'm learning from examples. There's a reason why we don't learn everything from examples. There is a reason why we actually use background knowledge. So that's something that's worthwhile keeping in mind. In the field itself, one of the hallmarks of the human intelligence is the seamless interplay between tacit knowledge, which you can only learn from examples, and you don't quite know how to explain, and the explicit knowledge for which you have essentially a sort of recipes. And combining them is something that's a big direction for AI. I would skip over this interpretability thing. This is actually one of the interesting questions about it is the machines that work very well in image recognition fail in ways that you have no idea. Okay, so for example, these are well-known examples. This is a school bus. I just added some noise so that it looks like that, and you obviously can see that this is an ostrich, right? Similarly, this is a dog, and then this is a dog, and then it becomes an ostrich. And to me, coming from South India, the most sacrilegious thing is apparently you add some noise to the tempo, it becomes an ostrich too. It is possible that unbeknownst to you, the world is full of ostriches. Right? It's also, let's not get too confident and cocky. It's not like our visual system is particularly good. Okay, we have visual fallacies. I don't know how many of you have seen this. Have anybody seen this? This was a picture that led to a lot of uproar in Norway, our favorite immigration country, where essentially some people looked at the picture here and said, oh my God, immigrants, these Muslim women and burqas are coming and taking over Norway, we need to stop this. And there was a large amount of hue and cry. Of course, you can see, you may think that these guys are bigots, but you can see where they went wrong. You know why they thought this might have looked to some people from certain angle as a burqa clad women. Whereas for the life of you, you can't explain why that temple looked like an ostrich to the network. If you can, then you are in very good shape because you can converse with machines. So that's a very useful thing. And the last thing that I guess I'll have time to talk about is the thresholds for human level intelligence. There are important ones. There's common sense, incompleteness, learning from very small number of examples, and also interaction with humans. And of these, given the time restrictions, I'll just talk about common sense and then human thing for a little bit, and then you can just stand up and also. Okay, so common sense is basically what we all think we have and our friends don't. My example for this is explorer Magellan went around the world 3 times. One of his trips he died. Which trip did he die? How do you know? And those people who feel particularly smart that they know the answer, of course, they are also in trouble. But in general, we know these things. Machines don't know this. Okay, so common sense is the glue that sort of takes partial specifications and make them into complete specifications. AI systems don't yet have that. And the last thing I want to mention is human AI collaboration. As a field, there are people from NASA here. As a field, we have been extremely happy sending robots onto the Mars, where there are no people anywhere nearby. Are very happy when we beat humans in various things, chess, poker, Go. We never seem to like to take pride in helping people. Okay, so I sort of think of John Lennon, who said, "You want to help humanity, it's the people." I personally think that this is the kind of headlines I'd like to see about AI. AI helps old lady cross the street, plays with kids, cooks food, hangs around, stands drama. That's fake news right now, because people don't talk about it. And part of the reason they don't talk about it is that in the research community, people were worried to some extent that putting humans in the loop might be cheating the problem, because the humans will start solving the problem, and what is there for the machine left to do. It turns out that's actually a wrong way of looking at it. We have the brains we have, and as much as we feel sometimes very stupid, we have too big a brain to run away if all we need to do is to run away from the lions and tigers. And really, the one evolutionary speculation is that we have the brains we have because we are continually monitoring each other's mental states. And when the machines have to work with humans, they need to monitor human mental state. And that actually opens up an entirely new set of challenges. Mental state without actually poking into their brain, which is getting information about what you are thinking, what your goals are, indirectly. And so, in fact, in the intelligences that I showed you before, I kind of skipped over emotional and social intelligence. And some of you are old enough to remember this guy, Rodney Dangerfield. Those intelligences never got much respect in AI. Because it turns out that you never get a job for having emotional and social intelligence, but you will get fired from one because you don't have it. And so much of what I've been doing is in both my research as well as in evangelism to get human-aware AI systems being taken seriously. And I just gave a IEEE presidential address a couple of weeks back, actually February, and that's just that, and that's available. That you might. And it turns out that the entire intelligent agent architecture changes quite significantly if you wind up taking humans in the loop seriously. And I'll show you two of my videos because I have them, and then we'll be stopping. One is, for example, this is my own work from my group. Teaming between humans and robots requires the ability to model the mental state of the humans. That might happen either through language and normal modalities, or it can also happen with this guy, for example, wearing like an emotive helmet, which sort of does a simple, non-intrusive detection of brainwave patterns, but not anywhere near enough to completely read your mind. Okay, so that will allow you to read the robot to read what this guy is thinking, and you can also use things like HoloLens for the robot to tell the human what they are about to do. Okay, so project where you are going as well as read what they are trying. What's more interesting, and that's probably the last thing I get to do, you're going to stand, right, when one will stop, is that projection, dealing with humans not only requires you to model their mental state, but you also need to model their state of their mental model of what they think of you. It's a second order model. Of course, they may be infinite figures, but at least second order model is important. Because a lot of things like explicability, that is doing things that won't spook you, And explanation, which is trying to explain to you why I did something when you expected me to do something else, involve me reasoning with your model of me, which I have to learn indirectly and have to reason with that. So much of our work in the lab, for example, involves doing this explicable behavior. So in this particular case, this robot is trying to go from one place to other. It turns out that a particular short path is blocked, and rather than just take a different path, it tries to unblock the path because that will help the human expect what it's doing. If it doesn't do that, then it needs to give an explanation to the human saying, explanation of the path from one place to other is actually closed. Explanation is about the other person's mind, not about your mind. So you should be talking to yourself and feel very good about it. So that's something that winds up being important. And in fact, you can also trade explicability and explanation. Together. And then that's basically my second part. I'm going to probably stop now. Okay, so there are things that I was going to talk about. I'll just show you this slide and I'll stop. Which is that there are lots and lots of good things that AI can do for you. You know, improving, you're making automation of various jobs and improving your lives. But the same technology can also lead to a lot of other problems. For example, you can create fake reality, you can manipulate reality, you can do biased decision making. The people are worried about technological unemployment, for example, and also, of course, people like people like Hawking are worried about super intelligence, unsuccessful human AI collaboration where the AI turns against you. That I don't particularly worry about, but these we do worry about, and in organizations that I work with, AI as well as Partnership for AI, have been looking into how to manage some of these risks while dealing with the rewards. So I'll just stop here. Thank you.
Thank you. So we've got 5 minutes into the reception this evening.
Okay.
Rao will be around tonight, so feel free to come back and ask questions.
Thank you.
Thank you.
Thank you.